Thank you, Bob. So there was a fair amount of discussion yesterday about radiation. It seems like radiation is a flashpoint, so to speak, on topics related to deep space and to Mars. What's interesting is we had an article come out in Science Magazine the end of May, and out of the 50-some articles in the popular journals and literature and news sources, maybe 2 or 3 of them kind of understood the subtleties of it. It's not necessarily the mission killer that people like to make it out to be, but that's what gets the headlines. So I'm going to talk today about observations from the radiation assessment detector on the Mars Science Laboratory. One of the things that's really exciting is that we're now actually making measurements on Mars of the radiation environment, and we actually got some great measurements during cruise as well inside the spacecraft, which I'll talk about shortly. So to start off, like all large projects and NASA projects these days, RAD is a collaboration both between Southwest Research Institute and the University of Kiel in Kiel, Germany. So it's an international collaboration between the US and Germany, but it's also a collaboration between the human exploration side of NASA, HEOMD, and the science side of NASA, SMD. And it's actually one of the first instruments that's funded by the human exploration side, but on a science mission. And I think it's the beginning and hopefully the way of the future of combining science and exploration, because I think together that's the best way to really gain support. So just a very brief overview of the Mars Science Laboratory, the Curiosity rover. There's 10 instruments on Curiosity. RAD is the one sort of, well, you can't really see it. I'll show a picture of it later. It's in the middle. It's a small instrument. It's really about the size of a blender or an espresso machine. There's 9 other instruments that do sampling of the soils and also atmospheric monitoring. The primary objectives of MSL are to assess present and past habitability of Mars, which means searching for the elements needed to sustain life, obviously water, but also carbon-based materials. But it also means to characterize and study life-limiting factors, which includes radiation. Radiation is, in terms of if you're looking for microbes or evidence of microbial life in the early days of Mars, you do want to understand what the radiation environment is now and was then, so it has impacts on the preservation of biosignatures in the rock. But also for sending humans there, we need to understand this, and that's why I'm here today to talk to you about this today. Just a brief overview of Curiosity. Maybe all of you are fully aware of this, but Curiosity is the largest rover in the NASA Rover family. There's kind of a picture of it compared to Spirit and Opportunity. This is the size of it compared to humans, so it's actually quite large. It's really, people say it's like a Mini Cooper, but I think it's more like an SUV. It really is quite a large rover. And here it's all assembled in the descent stage and the cruise stage and everything like this with respect to the humans, and it's quite large. So on November 26th, the day after, well, 1 day after Thanksgiving in 2011, we launched from Cape Canaveral with a picture-perfect launch and an orbit insertion, which was excellent. And this is just a location of the Curiosity landing site on Mars, for those of you that know all these different locations. From the RAD point of view, it's not so much the location of where it is as it is the altitude of the amount of atmosphere above it that affects the radiation levels on the surface. This is kind of a view of the landing ellipse in Gale crater. It's sort of at the bottom of this 5-kilometer high mountain called Mount Sharp, and it's sort of also at the base of this fluvial fan or outflow that we've now determined was flowing water at one point, a river coming from the crater rim. We got some spectacular imagery. One of the best things these days is that we have multiple spacecraft all supporting same objectives. So this is a high-rise from MRO image of the parachute and MSL as it's descending down towards Mars, and it's quite spectacular that we had everything aligned just right to be able to take pictures from orbit to observe to watch it descend as it goes towards the planet. And I think hopefully all of you have seen the 7 minutes of terror from JPL. Clearly the landing was a nail-biting enterprise. This is actually images of the heat shield separation from the MOLI or the descent imager on Curiosity, as we're going through the atmosphere at several Mach speeds. This is the dust trail that's being kicked up just prior to landing, and it actually is quite a significant landing event. We've been finding debris kind of scattered all over the Mars surface. When we send humans, we won't have quite the same. We won't be using a tether in the same way that we did MSL, but there's still, the issues of kicking up all the dust that we had. And then this is the first image that we got landing on Mars. Oops. Oh, not quite the right image. There's the first image landing on Mars. So that's Mount Sharp in the background. And actually, the next day we got a much better image of the canyons and the buttes that we have as our playground over the next few, hopefully 10 or more years. Basically, Curiosity is doing great. All the instruments are working very well, and we're now headed towards Mount Sharp. In July, we finished exploring some regions out in the plains, and now we're on the high road, on the highway, basically headed towards Mount Sharp to explore the buttes and canyons and valleys of Mount Sharp, and that proves, I think that's going to be very exciting, because all this sedimentary structure is a lot like what you see in the Grand Canyon, and you can learn so much about the geologic history of the planet by studying that sedimentary history. This is also one of my favorite images. This is sort of one of those Back to the Future moments where the landing site was right here. Here you can see the scar marks from the descent stage, and then the rover lands straight down here, and then it drives away, and you can see these tread marks, which basically just start in the middle of nowhere, and then they drive out. So this is the last time you'll see an image like that, because otherwise you'll have tread marks coming and going from where you were, and here we landed, and now we're driving away. So this is a picture of RAD on the surface of Mars in Curiosity. This is actually a picture of the window, the protective window made out of mylar to keep it from getting damaged. In fact, you can see the dust, debris, all the little small pebbles and rocks on the surface of the rover, and there's actually a teeny little pebble on the surface of our window as well. Fortunately, none of those rocks broke our window. So, but there was one casualty. I think one of the wind sensors on the REMS instrument was impacted by some of these dust particles. But for the most part, amid all that debris, everything survived quite well. So the question is why do we need to be making these measurements? And this is just a tutorial. If you may already know all this, but fundamentally there's two reasons why the radiation environment on Mars is fundamentally different than that on Earth. Mars doesn't currently have a global magnetic field. It may have had in the past, in its early days, say 3.5, 4.5 billion years ago. That's not clear. There's signatures of these remnant magnetic fields which suggest that there may have been one. So the discussion yesterday about the InSight mission hopefully may give some insight, so to speak, about what happened to the magnetic field and the early days of Mars evolution in the Noachian and pre-Noachian time. What is it that happened in the interior of Mars that made it lose its liquid magnetic core? The other is it's got a very thin atmosphere. So as a result of losing this magnetic field, it lost most of its atmosphere. And Mars has about 1% the thickness of the Earth's atmosphere. So basically, Mars is exposed to the deep space radiation. I'll talk more about the details of that shortly. But what kind of radiation are we talking about? Well, we're talking about galactic cosmic rays, which come from outside the solar system, thought to be coming from supernova remnants. They're very high energy, as Bob mentioned yesterday, but relatively low flux. They vary slowly over the solar cycle. These are this insidious kind of radiation that's just always present, and it's hard to shield against, but it's there, and you need to know about it and when you can shield it, but it's very difficult. And then there's the solar energetic particles, which are sporadic. They also depend on the solar cycle, but they come very episodically when there's a flare or a solar particle event, which happens typically on the ascending or descending phases of the solar cycle. You can get these events that happen. They come very quickly, on the order of minutes to hours, and they can last hours to days. and they can increase the radiation dose by several, if not many, orders of magnitude. These are the ones that they're hard to predict. Improving our ability to predict them is one of our best opportunities for improving safety in terms of the radiation for deep space travel. So I'll talk about that all shortly. This is kind of a view of the solar cycle variations. You can see, what we call sunspots look like these orange glowing areas in ultraviolet images. They're called active regions in the solar physics community, and they vary with this 11-year solar cycle. And in the solar particle events, this is kind of a coronal mass ejection as a result of a flare on the surface of Mars, on the surface of the sun, and they expand out in the solar system. So this is the two types of radiation that we're dealing with. So the charge for RAD was, back when the MSL payload was being formed, was to build an instrument that fit within about a kilogram box that could measure and fully characterize the full spectrum of radiation. That means charged particle radiation from protons all the way up to iron. It also means neutrons and gamma rays. It's quite a tall pole, because typically instruments on other satellites are 10 times the mass, 10 kilograms or more. RAD is the size of a blender, and it's about 1.5 kilograms or 3 pounds, and about 4.2 watts when it's operating. And we have basically two types of detectors, one to measure charged particles and one to measure neutral particles inside the detector. And as I mentioned, we measure protons and iron. We measure particle spectra from protons all the way up to iron. So protons, helium, lithium, all the way up to iron in about a few MeV up to a few hundred MeV per nucleon, which is basically the energies that are relevant for biological tissue, that do damage to biological tissue. And then we measure neutrons from a few MeV up to a little over 100 MeV. And the low end, these are also the range of energies where neutrons do damage to biological tissues or ionized biological tissues. And these were limited on the low end because of the RTG, which basically provides a large background below a few MeV. This is just a cross-section of RAD for those of you that are interested, but we have basically an electronics package with three cards, a digital board, an analog board, and a power supply and telemetry board. And basically, there's two types of detectors. There's a charged particle telescope with 3 solid-state detectors, which are used to measure and characterize the charged particles. And then we have 2 different types of scintillators, a cesium iodide and then a plastic scintillator with an anti-coincidence shield around it to measure the neutral particles. This is kind of a view of installing RAD below the. This is the rover's turned upside down, so we installed RAD from underneath the belly. You can see the size of it compared to the humans. And then when we're on Mars, it's designed to be very simple in its operation. We basically, we're autonomous. But with all the, not 10 instruments on the rover, we really wanted to be simple. We wanted to just turn on and do our own thing and let all the other instruments, jury for telemetry and uplink and commanding and all these other resources. Basically, RAD is autonomous. We have a little processor which turns it on, takes data for a period of time, stores the data, puts itself to sleep if we need to save energy, and then at a predetermined amount of time turn ourselves back on. We could do this periodically. Turns out energy is not as big of an issue on MSL as we thought, so we're actually running with a 100% duty cycle. But the ability of RAD to be completely autonomous was used during cruise, and is a really good feature in the event that as our RTG starts to lose its efficiency, and if energy becomes more and more critical in terms of sharing energy with the other instruments, then we can operate very autonomously. It also has a large memory. We can store about 4 weeks of data on it, so we don't even have to communicate with the rover for quite a long time. So one of the things we realized about a year before launch was that we're sitting inside MSL in the same way that a future astronaut might be inside CEV or the Orion manned vehicle or the Mars 1 or or exploration Mars vehicles, or any astronaut crewed vehicle with some amount of shielding around it. So taking observations on the way during the cruise on the way to Mars was actually not an unreasonable proxy for the environment that an astronaut might experience. The question is, what's the amount of shielding there? So, most instruments, energetic particle instruments that are in deep in space, like STEREO or ACE or other satellites, they want to measure the raw, pure radiation environment, and the instruments are mounted on the outside of the spacecraft. This was different because this wasn't our primary intent, but we were buried inside the spacecraft, and that's a unique vantage point. So 10 days after launch, we were able to turn RAD on, and we operated for about 7 months collecting data of the radiation environment inside the spacecraft. And this is a plot of the dose rate as a function of time over those 7 months. And what you can see here, we have a dose rate in silicon, which is mostly susceptible to charged particles, and then we have a dose rate in plastic, which is sensitive also to the neutral particles. So the plastic dose is slightly higher than the silicon dose, but they both increase when there's a solar particle event, for example. So this was the ascending phase of solar maximum. We were actually, from our point of view, we were fortunate to observe 5 large flares or solar particle events, which are quite interesting to study and extremely important to study, in addition to the background galactic cosmic ray level. So this what looks like a background is really the galactic cosmic ray level during cruise, and then these 5 spikes are the dose increases for these short solar particle events. So we really were able to characterize both types of radiation inside the spacecraft, and that's pretty exciting. So for example, on March 7th, there was a flare on this side of the sun. Here's the location of Earth. Mars out here. MSL was not, we were still only part of our way to Mars, and then the other planets. And this is actually an interesting time because there was an alignment between Messenger around Mercury. Several of the STEREO spacecraft A and B were over here, but there was an alignment with an MSL and the Earth-based satellites. So we actually have observations from all these different satellites to look at and characterize what we saw during this big solar particle event. So, for example, there's the weather satellites around Earth called GOES. They have a proton monitor, energetic particle monitor, which measures solar particle events that hit Earth. And you can see the plots of those data, so you can see this increase. So if this is the flux rate on the detector in terms of particles per centimeter squared per second per steradian, you can see them increase in the high energies, for, 1, 2, 3, 4, 3 to 5 orders of magnitude. Inside the spacecraft, these are the RAD data, and they increased by about 1.5 orders of magnitude. So there was shielding from the spacecraft, but not perfect shielding. We still saw these events, but they were, instead of increasing by 5 orders of magnitude, they increased by 1.5 order of magnitude. Here's a slightly different way to look at it. We're focusing on this one event. The red line denotes observations from the SIS instrument on the ACE spacecraft, and we took the data that was most comparable to RAD. So this would be sort of like the pure particle environment in space, and then the RAD measurements in black would be the shielded environment inside the spacecraft. So you can see that the pure environment, 1, 2, 3.5 orders of magnitude increase. The RAD levels, 1.5 orders of magnitude increase. So we had effective shielding. It could be more effective, but you can see that there was some benefit from the shielding. I'll talk more about that in a second, and the question is to understand exactly how much and how to improve that. Just tallying it all up, we had, out of these 5 solar particle events, we basically saw that the solar particle events contributed about 5% from these 5 events to the total dose, equivalent dose accumulated during cruise to Mars. So you think, okay, the major contributor is these galactic cosmic rays. They're hard to shield against. Even the best shielded spacecraft is going to have a difficult time shielding against these galactic cosmic rays. The solar particle events, the ones that we can shield against, they still contributed 5%. Well, that depends on, it was just happened to be this time this period of time where these 5 events contributed 5%. So what you really need to do is try to understand what the variability of that could be. If there's a really large extreme event, it could be an order of magnitude more than this. It could be 50% of the total dose. If it was a quiet time, it could be 0. It could be 1% or less. So this is the challenge, and I think and we'll see as I go through in the talk that it's these solar particle events that are the challenge, but also the things that we have the best likelihood of being able to mitigate against. This is a study that was presented at the AGU meeting last December. This is interesting because it's a table and it's maybe not legible from the audience, but what this is some of the largest events seen in history since the beginning of the space age. They're called ground level events that we can actually see with neutron monitors from Earth. There's some big ones in 1956, 1959, 1972. There's a lot of publicity about there was a large event sort of in between 2 Apollo missions, and if that event had happened during one of the Apollo missions, the outcome may have been different. But what's interesting to note is this last column, the dose equivalent of 5 grams per centimeter squared of aluminum shielding, which is, okay, that's lightly shielded, but it's some level of shielding in millisieverts, is on the order of, for this largest event, could be 500 millisieverts, which could be really large. Okay, well, that's one event out of all the ones we've seen in the last, I guess, almost 60 years. So that's not very likely probability, but it's out there. And so when you're doing mission design and mission planning, you need to take all these things into effect. More likely you get things that might be a few hundred millisieverts. If you compare those to my table before, that means they could be 10 or 20 or 30% of the total dose during the cruise. But that doesn't happen all the time. I mean, we have maybe a dozen events over the course of 30 years, or 40 years. No, longer than that. Close to 50 years. So, but that's the challenge. That's the way you have to look at these things. So what we did then, we had to model what the shielding was in the spacecraft. This is the field of view for the charged particles. You can see all the stuff inside the spacecraft. This is the point of view of RAD. You can see the hydrazine tanks. There's actually the parachutes over here. A lot of this stuff. It's very inhomogeneous. I think the idea when you send a human crewed mission would be that you would want to have very uniform shielding, as uniform as you can, with a constant level of shielding, 10 or 20. As thick a shielding as you can, but shielding costs mass. So a lot of the ways people are thinking about it is you have materials that double as both shielding but also serve other purposes. Water is a very good shield, so if you don't have what you can either shield your entire spacecraft, or you can have shelters like the sleeping quarters, which are surrounded by either the working water or the drinking water, or both really. The water provides a very good shield. So if you had 10 centimeters of water around your sleeping areas, that was a relatively effective shielding. And if that was uniform, you would have slightly better than what we have here. This is kind of a cross-section of the modeled shielding. It turns out MSL had about 24 grams per centimeter squared average shielding, but it also had very high shielding around the hydrazine tanks. Hydrazine is a very good shield. It's also very reactive, but you could surround your sleep around the tanks. That's good. But then also some areas where it's weakly shielded. So if you compare that to, say, space station, that's not so different than space station. Space station wasn't designed to be uniformly shielded. It's relatively inhomogeneous. Some compartments, some areas are less shielded than others. There are polyethylene sheets that astronauts can use, and they can go to certain quarters when there is a large event. But we're actually building a RAD to go on space station now, and they're going to use it as an area detector, and they're going to take it around to the different rooms, the Russian module, the Japanese module, the American modules, and characterize what the environment is in these different modules. So you want to have uniform shielding. You could likely improve upon what we have here, but the idea here is that there is some level of these solar particle events that come through, and if you don't have them well shielded, then you have to deal with those. One of the primary objectives of RAD is, these are the first measurements that have actually ever been made. As scientists, you can have theories and models and ideas all you want, but until you actually make ground truth measurements, you don't really know the answer. So these are the actual first measurements that were made, and we're just now starting to compare them with the models. There's at least a half a dozen different radiation transport models out there. And so comparing our actual measurements with these models would be ways to validate the models, and in the case where there's areas where they aren't consistent, to improve upon them or correct them or to make them better. So, one of the primary objectives of making these measurements is not that we don't have any idea what the radiation environment is. We have lots of ideas. There's been studies for many, many years with models and ideas about it. But what we have never done was actually measure it. So with these measurements now, we can go back and validate these models. And one of the interesting things, which I'm not showing here, is that RAD actually takes energetic particle spectra, meaning we get spectra of the protons and the helium and the lithium, and we're going to get spectra to compare with these models. And that's the real precise way, because there's lots of ways you can add up different energetic particle spectra to give you a certain dose. Dose is really not the best way to determine, or dose equivalent to determine what the potential biological damage would be. This is just an example of some of the different galactic cosmic ray models that vary all over the place. The purple are actual data from ACE, and then these other plots are varying models. And what's interesting is that when we had this really deep solar minimum back, well, not so many years ago, back around 2009, 2010, this was the longest and deepest solar minimum that we've had in 100 years. These models don't do very well to predict that. And actually at solar minimum is when we have the greatest risk of, or the greatest cosmic ray flux. So, from a strategic point of view, you want to go in solar maximum where the galactic cosmic ray flux is lowest, but you also want to be lucky so you don't get any really large solar particle events. So it's a combination, because if you go at solar minimum, you're increasing your insidious background dose of GCR. So you need to understand the solar cycle, and you want to be able to monitor this over time. This is sort of a comparison bar chart that we put together to talk about what these kinds of levels are. This is just the level of the galactic cosmic ray dose for 6 months during our cruise to Mars inside the spacecraft, compared to this one, which is space station. So say 100 millisieverts for dose equivalent for space station versus about 331 for on the way to Mars. So about 3 times the space station level. One could certainly improve upon the shielding, but that's what those numbers are. Comparing this to things that we know, just the background radiation level living, well, actually, I don't think this is in Denver. I think this is at sea level, so it's much lower. Denver is another factor of 2 higher than that. We got to pay something for the privilege of living in Denver. But if you add all the U.S. sources up, it's about 5 millisieverts. A CAT scan is about 8 or 9 millisieverts. So the dose we're talking about is like 5 or 6 CAT scans, or a CAT scan every 5 or 6 days. For radiation workers, it's about half of that a space station. But these are just for routine things. There's lots of risks when you consider a mission to Mars, and for something as important as an exploration type of mission, or an event such as going to Mars, as Bob said yesterday, it's going to be talked about for centuries to come, not just the next few years. So this is just a summary of the cruise observations. The things that are still in progress, we actually have several publications that are just in press right now. So I'm not showing all of these data, but we have an energy spectra publication coming out in JGR. Also the neutrons contribution, the albedo neutrons, as a result of these charged particles smashing into the atmosphere. Well, also during cruise, but into the spacecraft, generates these secondary neutrons. So understanding the contribution from the neutrons is an important element of this, and we have a paper that's getting ready to come out during that. So then we finally land on Mars, and this is one of the things that I think is really cool, is that exactly 100 years to the day from the date that Victor Hess discovered cosmic rays from his hydrogen balloon in Austria in August 7th, 1912, we made the first observations of galactic cosmic rays from the surface of another planet. So it's kind of amazing, the progress over the last 100 years of discovering for the first time this type of radiation, this type of physical phenomena, and then 100 years later to be making these measurements from the surface of another planet. I think that's serendipitous, and that's pretty exciting for us. This is one of our first plots. This is actually the first three and a half hours of observations. What was interesting is that we could actually, when we ran in our highest time cadence with RAD, which we don't always do because we're telemetry limited with the mission, so we bin things into histograms and sum them now. But when we were running in our highest time cadence, we could actually see individual high energy particles hitting the detectors, and we could actually measure the increase in the dose rate from those individual events. You know, now as we accumulate data over the last year, we're summing all these things together. One of the things we're finding, though, that's really interesting, there's a lot, you know, is that the radiation RAD, but the radiation levels on the surface of Mars are very sensitive to atmospheric variations. As the atmosphere heats up and cools every day on a daily basis, the pressure goes up and down. The total column of atmosphere goes up and down by on the order of 10%, and actually the radiation dose on the surface of Mars goes up by about 1.5 to 2%. So we can actually measure that. That's quite interesting. Another thing is that we find is that the charged particle dose on the surface is anti-correlated with the neutron, the neutral particle dose. The charged particles are the direct radiation coming through the atmosphere, and the thicker the atmosphere, the less charged particle dose, but it also has more interactions in the atmosphere, and that actually increases the neutral particle dose. So we actually see an anti-correlation between the charged particle and neutral particle dose on the surface. So that's just one element of the phenomena that we're learning. I think that, you know, right now we have these first results from the first year of surface observations, which is in press with Science magazine. So it's embargoed. I can't really talk about all those data, but I'm trying to give you a summary or a snapshot of the idea of where we're at. And I think, you know, the significance is that these are ground truth measurements. These are the first measurements ever been made from the surface of another planet. Some of the things we're reaffirming or you know, that we feel relatively good about is our models aren't too bad. The average galactic cosmic ray levels are on the order of what we expect. I guess that's not surprising, but there are certainly surprises that we're finding. The variability, not only the daily variability, but the detailed comparison with the models is new and different, and that's going to come out in these papers. Also, the response to these solar particle events. We've only observed one solar particle event since we've landed on the surface, and it wasn't a very hard event, meaning it didn't have very high energy. But over the course of time, it's going to be very important to characterize what those events are, because those are going to be the defining events. Basically, and as we go towards solar minimum, then we're going to see, you know, how things increase, and that's something. If we get another deep, long solar minimum like we did in 2009, it'll be very important to make those measurements. Right now, we're about here. Actually, we're a little further. We're right about here in the. I need to update this plot, but we're right about here, and we're still basically in the peak of solar maximum. And over the next few years, we're going to go towards solar minimum. So, what are the lessons learned from this? Well, one of the things is that, you know, we really need to pay attention to the space weather and monitoring and looking for these solar particle events. You know, here's the location of RAD on Mars. Here, this is a particular day. This was. It doesn't show the day, but it doesn't really matter. Here's Earth in heliospheric longitude. Here's Mars. Here's a couple of other spacecraft. But, you know, back a few months ago, Mars was on the opposite side of the sun from Earth. So if you need to do your own space weather monitoring, you need to do your own prediction of solar particle events. You need to do your own warning of solar particle events when they come. We need to also have a better understanding of these events, because these are the ones that are going to define how we how we can maximize the protection for our astronauts, not only during cruise, but on the surface. So we're going to have to develop the capability to do that independently. So I guess the takeaway points would be, you know, I don't believe that the radiation is a mission killer. I think that, you know, I think we will go to Mars. NASA's committed to going to Mars, and to going, you know, it has missions to the asteroids which are being planned, and you know, everyone I talk to is committed towards, you know, going to Mars by the 2030s. We have private companies that want to get there much sooner, and that's very exciting. But I don't think radiation will prevent these things from happening. I think but it's one of these risks that, you know, you have to do due diligence. You have to be aware of it. You have to characterize it, and you need to understand it. You need to monitor it. So in this sense, RAD is serving a very important role of making these ground truth measurements to validate our models, to improve our capability to predict these things or to see when they're coming. And when we do go to Mars, we're going to have to do our own space weather monitoring. We're going to have to do our own protection for our astronauts as we go. And I believe that it's these extreme solar particle events, the once-in-a-lifetime type events, the once-in-a-100-year events that are the biggest risk. Now, if you compare that to the risks of EDL or the risks of other absolute mission-ending failures that one has on a mission of this magnitude, that's small. But, the risk of getting lifetime cancer, well, that's lifetime cancer, and it's a few percent increase, even if it's 10 or 15% increase over your lifetime compared to 20 or 25% from living in Denver. That's a relative thing. It's not necessarily a mission-ending scenario. But a large solar particle event, if we got an event like 1972 or 1956, which periodically happens over time, and if you're in the wrong place at the wrong time, if you're during cruise and you don't have adequate shielding, or if you're on a spacewalk on Mars and you're outside your rover, which hopefully would be shielded, you may not have sufficient shielding, and you need to be aware of this and protect against it. So we need to continue to monitor the space weather and the environment, not only at Mars, but throughout the heliosphere. This is an area of growth for understanding, because as we explore into the heliosphere, this is going to become more and more important. And then there's the certain important elements of crew monitoring and storm shelters, which I think everyone can appreciate and understand. So that's really it. I'd like to thank NASA and the human exploration, and both the human exploration and the science mission directorate sides of NASA for their support of RAD, and it's been an overwhelming support, as well as JPL. Everyone at JPL has been fantastic, and RAD is working great, and hopefully we'll get a whole solar cycle of observations on Mars. So thank you very much. Any questions? Oh, good. I'll start with Bob.
Hello? Yeah. Have you taken measurements of solar particle events while Curiosity has been on Mars? In other words, how much attenuation of them has there been from the Martian atmosphere of solar particle events?
Right. So we've seen one event in the last year from the surface of Mars. That's one of the topics of this paper that's coming out in Science. So I'm not going to discuss it too much. One could say just at the zero order level, the shielding provided by the Mars atmosphere is on the order of 16 to 20 grams, which is not so different than the shielding during space. You have one advantage of being on the surface of Mars is that it's a planet, which only has 2 pi steradian effective field of view out to space. So just at the zero order level, that's reduced from your deep space measurements. But what's interesting is these solar particle events are all over the place. One of the things we're also finding is that, this is maybe a little bit technical term, but there's weak events, meaning not very high energy, and then there's hard events, which have very high energy. You can have an event with your maximum energy being 50 MeV protons, or you can have one with 300 MeV protons. Those hard events are the ones that are going to make it all the way down to the surface. It takes about 150 MeV proton to actually make it all the way to the surface without getting stopped in the atmosphere of Mars. So these hard events make it down to the surface. These weak ones, we actually see slight decreases in the actual flux because of a concept called a Forbush decrease, which basically the magnetic field of this storm kind of envelops the planet and shields it against the cosmic rays.
Yes, you show a figure which shows that the level on the surface of Mars is about half the level during cruise, which can be explained by the geometric situation. But why don't we see the effect of the atmosphere? Is it because the RAD instrument is shielded inside the spacecraft during cruise and not shielded on the surface?
That's basically correct, yes. It's shielded inside the spacecraft during cruise. On the surface, we're not shielded at all.
Okay.
But the atmospheric shielding is
About
not
the same.
completely different. It's not exactly the same. And this, I hate to have to say this because I really wanted to talk about all these data here freely, but it hasn't been published yet in science. And
Okay.
they're very careful about this. But it's on that same order, yeah.
Okay, we have time for one more question.
This may be a silly question, but when I was a boy, I was given a wristwatch that had the glowing hands that I think was radium. And I understood that to be radioactive, and subsequently I think it was. Just trying to put this in layman's term, the amount of radiation I may have received from that watch versus what you have, I guess, in the cruise phase, comparable, completely off the map, where would you put that, just from a layman's perspective?
I can't say exactly, but I'd say it's pretty small. I would guess it's pretty small, yeah.
Okay, great. Thank you, Dr. Hassler.